Hey everyone, I hope you're doing well. Since there was a lot of interest in combining animations with IK for my weapons equipment system using IK tutorial, I've decided to create a small series of tutorials focusing on Unity's animation system and its animation rigging package. In the upcoming tutorials, we will cover everything from creating and using Animator controllers, working with animation clips, handling animation events, to setting up multiple rigging constraints using the animation rigging package. By the end of this series, you'll have a solid understanding of how to use Unity's animation system to create realistic and dynamic animations. We'll cover how to manage rigging constraints, work with weighted transform arrays, and show practical examples of IK in action, such as aiming systems and examples inspired by AAA games. Notice here how the upper body feels natural and moves fluidly when aiming. Here is another subtle but interesting example of using inverse kinematics in games. Take a look at how the hand is placed correctly on the stone while she is moving towards it, and notice how the head and torso are also bending according to a specific target. We will work on implementing something similar together soon. This is part 1 of a series where we'll cover a lot of content about Unity's animation system and inverse kinematics using the animation rigging package, with engaging examples. In this episode, we'll go through 4 different examples to learn how to combine IK and keyframe animations, utilizing the multiple constraints provided by Unity's animation rigging package. Given the extensive topics we'll cover, this series won't be a step-by-step tutorial. Instead, I've prepared everything in advance and will walk you through the process and code, explaining each step in detail and discussing different approaches to some examples. Now let's get started without further ado. The Unity animation system, sometimes referred to as Mechanim, is a powerful and flexible tool for animating characters, objects, and environments. It offers an easy workflow and setup for animations of all elements in Unity, including objects, characters, and properties. The system supports humanoid animation, allowing animations to be applied from one character model to another, a process known as retargeting. Unity's animation system has special features for working with humanoid characters. The avatar system is how Unity identifies that a particular animated model is humanoid in layout, in which parts of the model correspond to the legs, arms, head, and body. By creating an avatar mask for a humanoid character, we have the ability to create animations that only affect the upper body of the character, for instance. We will see this together shortly. By the way, Unity has another animation system, which is the legacy animation system. It uses the animation component. According to Unity's documentation, the legacy animation system can provide better performance for simpler animations with few animation curves, such as simple UI animations. Now let's explore the key components provided by the Mechanim animation system. I will also demonstrate other useful animation features as we progress through this small series. The first component is the Animator controller, which controls the flow of animations based on parameters and state transitions. It allows you to create complex animation state machines and manage the logic for transitioning between animations. The Animator component is attached to a game object to control its animations, using an Animator controller to determine which animations to play and when. This component is essential for any animated character or object, ensuring smooth and coordinated movement. Animation states represent the different animations within an Animator controller and define specific behaviors or actions. These states can transition between each other based on conditions and parameters, providing a flexible and dynamic animation system. Animation clips are individual animation sequences that can be played by the animator. These clips can be created directly in Unity or imported from external tools like Blender or Maya, giving you the flexibility to use existing assets or create custom animations. Animation events mark specific points in an animation clip to trigger events or functions in scripts, allowing you to synchronize gameplay actions with animations. For example, you can trigger a sound effect when a character's foot hits the ground, or spawn an arrow as we will do in our case. Finally, blend trees enable blending between multiple animations based on parameter values, creating smooth transitions between animations like walking and running. They are particularly useful for achieving realistic and fluid character movement by blending animations based on speed or direction. As mentioned earlier, I've prepared 4 different examples to explore. Here's the plan. I'll start by explaining and showing the final result of each example to give you a clear understanding of what we'll be doing in this video. Next, we'll set up the animation system, review the code, and connect everything. We'll then watch the results before adding any IK constraints to compare the difference once they are added, achieving the final desired outcome. Let's begin with the aiming system. For this example, we're using a bow and arrow instead of guns, just to try something different. Note that the setup process for a pistol, bow, or rifle is quite similar. The key is to understand the overall concept, which you can then apply to any weapon in your game. I downloaded this character from Mixamo, and as you can see, it already has a bow and arrow. We'll need to control when to show and hide the bow, as we only want it visible when the player enters aiming mode. Let me show you the final result and explain what needs to be done to achieve the perfect outcome. First, as you can see, when the player is in the default state, the bow is hidden. When I press the spacebar, an equipping animation plays to show the bow. Then, holding the right mouse button enters aiming mode, triggering an aiming animation. Additionally, we need to smoothly adjust the camera location. Enhancing the aiming experience involves damping the player's movement, applying rotation as we look around while aiming, and more, which we'll discuss in the code section. Now watch how the entire body moves and bends while aiming, including the torso. We'll also add constraints to both hands to make the aiming appear as natural as possible. Although this video focuses on animations in IK, I've included a simple projectile motion code to shoot the arrow, which we'll review later. I couldn't find a suitable shooting animation on Mixamo, so once the player shoots the arrow, we revert to the equip animation. If you notice, this equip animation is stripped down to only the last couple of frames, as we don't want to equip the bow again while still in the aiming mode. I'll demonstrate how to strip specific frames from a keyframed animation. Lastly, pressing the H key will trigger an animation to hide the bow, returning the player to the default locomotion state. Okay, now that we understand the concept and how we'll implement the aiming system, let's begin by taking a closer look at the animations we have and setting up the Animator controller. All these animations are downloaded from Mixamo, and we'll review the relevant ones as we progress through this tutorial. For now, let's focus on the aiming animations. There are a few details I want to point out about these animations. Most of these animations were originally downloaded for a different character. However, since we're using humanoid characters, we can easily retarget the animations to another character. The first character didn't have a bow, so I downloaded a second version that includes a bow. Alternatively, we could also get a bow from the Unity Asset Store. Let's take a look at the different animations we're using for the aiming system. This is a simple idle animation used in the locomotion blend space. I chose this idle animation to match the equipping animation for the bow. Since we're using free animations, it took me some time to find good matches. This is the bow equip animation, which plays when the player presses the equip button. Initially, the bow is hidden, and we need to show it at the right moment during the animation. While we could use animation events to trigger the bow's visibility, I'll demonstrate how to manage this using coroutines in the code instead. This approach offers more flexibility over the entire animation process. We'll leave this for later and focus on the animations for now. For the aiming animation, notice how the starting pose aligns with the equip animation. As I move the indicator along, you can see the point where we need to spawn the arrow game object, exactly when the character places her hands in the arrow bag on their back. We'll use animation events to achieve this timing. This is the final aiming pose before the player can shoot the arrow. And we also have an animation for when the player exits aiming mode. In this animation, we need to hide the bow at the correct moment and transition back to the locomotion state. If you select any animation clip and choose the animation panel on the right, you'll find the animation clip editor settings at the bottom. These settings, particularly those for root motion, are crucial. But first, let's understand what root motion is. Root motion is a technique used in animation systems, particularly in game development, to drive the movement of a character directly from the animation data rather than relying on external physics or scripting to move the character. Essentially, root motion allows the animator to control the position and orientation changes of a character within the animation itself, ensuring more natural and accurate movement. Let's take an example. On the left, we have a walking in place animation where the character's actual movement, translation, and rotation is managed by scripts or physics, not by the animation itself. The animation shows the character walking, but the character's position in the game world is updated through code. This is referred to as body transform, which controls the character's movement through scripts or external inputs. On the right, we have a walking animation with root motion enabled. In this case, the character's movement, translation, and rotation in the game world is derived from changes in the root transform embedded within the animation clip. As the character walks, the animation dictates its movement, resulting in more natural and accurate motion. This is called root transform, which controls the character's movement directly from the animation data, allowing the character's position and rotation to be driven by the animation itself. By leveraging root motion, we can create more realistic and fluid character movements, as the animation itself drives the character's translation and rotation, reducing the need for external movement scripts. Now let's examine the animation clip inspector settings. The root transform rotation, root transform position Y, and root transform position XC allow you to control how the root transform is derived from the body transform. These settings determine whether specific aspects of the body transform, such as the Y position, become part of the root motion, trajectory, or remain part of the pose, which is referred to as baked into pose. This provides you with flexibility in deciding how much of the character's movement is driven by the animation itself compared to external controls. The first option is the loop pose. Checking the loop pose flag ensures animations loop smoothly by distributing the relative pose difference between the start and stop frames across the clip's duration. The second option is the root transform rotation. If we checked bake into pose, it will keep the orientation in the body transform. The root orientation remains constant. The based upon allows setting the orientation based on body orientation, original, authored offset, or manual offset adjustments. We can manually adjust the orientation using the offset setting where the motion is perpendicular to the body's forward vector, such as strafing. The red light here indicates that this animation should use the orientation from the clip. If it were green, it would mean that the animation clip's rotation is set to be baked. However, in this particular animation clip, I found it more effective to bake the rotation. For the root transform position Y, if we checked bake into pose, it keeps the Y component, vertical movement, in the body transform, suitable for most animations except those with height changes. The based upon options include original, mass center, or feet. When using feet, the root transform position Y will match the lowest foot Y for all frames, ensuring proper alignment during transitions. And here also we can manually adjust the animation clip height using the offset setting. And finally, the root transform position XC. Bake into pose here used for idles to prevent drift, maintaining the original position for smoother transitions. Now it's time to see how we can set up the animation controller. In the base layer, which is created by default, we have a simple locomotion blend space. It only has 3 states: idle, walk, and run. We use the blend space to smoothly transition between animations, blending between multiple animations based on parameter values named movement. Since this video is not about third-person locomotion systems, I won't get into how to set this up in code. The focus here is on the aiming system, which I created in another layer. Animation layers in Unity are used to manage complex state machines for different body parts, enabling separate animations for the lower and upper body, such as walking and aiming. To add a new layer, you can click the plus button above the Layers widget in the top left corner of the window. Clicking the gear icon on the right side of the window will display the settings for this layer. The weight property in the layer settings determine the extent to which a specific animation layer affects the final animation of the character. A layer weight of 1 means the layer is fully active, while a weight of 0 means the layer has no influence. Intermediate values blend the animations from different layers. I will talk about the mask shortly, but first let's discuss the blending options. There are 2 blending options: override, in which the layer's animations replace those from previous layers, and additive, in which the layer's animations are added on top of the previous layers, modified by the layer's weight. This is useful for making subtle adjustments or adding movements to an existing animation. Animation layer syncing enables you to reuse the same state machine in different layers. The timing checkbox adjusts the length of animations in synced layers based on their weight. The IK Pass option is a feature within the Animator component that allows us to enable and manage inverse kinematics. Once IK Pass is enabled, we can write scripts to handle the IK calculations. Typically, this is done in a script that implements the onAnimator IK method. However, with the Unity animation rigging package, we usually do not need to use the IK Pass option in the Animator component. The animation rigging package provides a more advanced and flexible system for creating and managing complex rigging setups, including inverse kinematics. The mask specifies which parts of the body are affected by the layer's animations. For example, a mask might specify that an upper body layer affects only the arms and torso, leaving the legs unaffected. This allows you to blend animations for different parts of the body. I refer to this layer as the upper body layer. Even though we apply the aiming animation as an override to the base layer, the reason for this is that if we take another look at the aiming animation, we'll find that there is lower body motion as well, only in the actual aiming animation. So, for instance, we could separate these animations. Ones with lower body animation could be placed in the base layer, and the ones with upper body motion could be left in the upper body layer to only affect the upper body of the character. However, in this case, I will leave all of them in the upper body layer and keep the avatar mask on the whole body, as we saw earlier. Before we continue, there are a couple of ways to implement aiming state machines in games. One way is to use a single aiming animation, and with the help of inverse kinematics, this looks pretty good, and this is what we are planning to do here. However, I personally prefer implementing aiming with an additive blend space using keyframe animations for all directions, and on top of that, we could use IK to modify the hand's positions and rotations, but since this video is about IK, we'll continue with this method. Let's go through setting up the upper body layer. This layer serves as an override, replacing animations on previous layers. By default, we want this layer to not interfere with the base layer, which handles the player's movement. When the player starts the game, the player should be able to move smoothly until entering the aiming mode. To achieve this, we create an empty state with no animations, and then transition from it to the aiming state machine. The aiming mode is controlled by a Boolean parameter called isAiming. When isAiming is true, we transition from the empty state to the aiming state machine. Now, let's take a look at what's inside this state machine. There are two main things to note. First, certain animations such as equip bow and disarm bow are played directly from the script using the crossfade method. It's important to remember that we need to toggle the visibility of the bow game objects while these animations are playing. We'll delve into this further when we move to the code part. The transition from the equip animation to the aim animation is controlled by the isAiming parameter, which we will set in the code. If the player is aiming and suddenly decides not to, we should transition back to the equip bow animation. However, the equip animation is too long and includes drawing the bow from the back at the beginning, so we don't need to repeat that part. To solve this, we will trim the last few frames from the equip animation and use them in the transition. I'll show you how to do that shortly. If the player decides to aim again, we should smoothly transition from the current pose by setting the isAiming parameter to true. Let me demonstrate how to remove the last few frames from the equip animation clip. In this example, I only use the last 4 to 5 frames, but you could also just use a single frame, but for a more natural look I chose to keep the last couple of frames. In the original animation, it's clear that we only need the last few frames. To achieve this, we can adjust the animation clip settings using the handles to modify the length of the animation to fit our specific needs. Something similar to what I've done looks good. However, make sure to create a copy of the original animation before making any edits, as we need both versions. Then, remember to hit apply. As for the disarm bow animations, as I mentioned earlier, they will be controlled by a script. Once the animation finishes playing, it will transition back to the empty state automatically. This means this layer has no influence on the base layer, and the player can resume movement using the locomotion blend space. Now it's time to take a look at the code. When I prepared these examples, I did my best to separate each example into different scripts to make it easier for you. All the aiming scripts are located on the character parent game object. For now, let's forget about the rigs and continue without IK so you can see the difference before and after. Most of the aiming system functionality happens here in the aiming handler script. Additionally, I have added shooting mechanics using simple projectile motion. We will look at this later. First, let's focus on the aiming system. I'll start by explaining the purpose of each variable. First, we need a reference to the camera controller script so that we can change the camera behavior while aiming. Next, we require another reference to the reaching out class, which we'll discuss later in detail. This reference is necessary in the aiming handler to stop the camera behavior while performing the reach out example. We also need a reference to the animator component to toggle the visibility of the bow that comes with the Mixamo character. This bow is embedded in the mesh, so we can obtain a reference to it using the skinned mesh renderer. I will discuss the remaining variables when we reach the IK part. To determine the exact aiming point in world space, we need to use ray casts. Therefore, we need to declare a layer mask to filter out collision results. We'll also talk about the aim target for the IK constraints later. We also need a recast hit info variable to hold important hit information and a ray variable to store the aiming ray that needs to be calculated. Finally, we have two booleans, one to determine if the bow is currently visible or not, and the other to indicate if the player is aiming or not. In the start method, we begin by storing a reference to the animator component in the animator variable. We also set isBowVisible to false to indicate that the bow is initially hidden. I also disable the skinned mesh render for the bow in the inspector. In the update method, we handle input binding and control the animation states. If the player presses the spacebar while the bow is hidden, we play the equip bow animation. To handle the animation duration and toggle the bow's visibility at a specific time during the animation, we use a coroutine. Let's take a closer look at the bow visibility function. This function requires several parameters: the animation aim to be played, the specific time at which the bow's visibility should change, and a boolean to determine the bow's visibility state. We begin by playing the animation using the crossfade method, which takes the animation name and the transition duration, set to 0.2, matching the state's transition duration in the animator controller. In order to toggle the visibility of the bow, we need to know the length of the animation at runtime. While we could store the animation length from the beginning by checking the animation clip length in the inspector, this is not ideal, especially when dealing with multiple animations. However, there are a couple of ways to achieve this, such as storing all the required information using scriptable object. Then we could fetch these information at runtime. Here we will fetch all the information we need using the animator state info method. When playing an animation using the crossfade method, we need to wait at least a frame to get this information. However, sometimes when the player switches back and forth between different states, we still haven't transitioned correctly to the desired state. To fix this, we will use a simple do-while loop to wait until the animator has transitioned to the new state. Once we have waited for a frame or a little longer, we will have the correct information about the state of the animation we intend to play, which is the equip animation. Then we enter a while loop. This loop continues as long as the time is less than the animation length. During this iteration, if the time exceeds the visibility time, we toggle the bow's visibility and set the is bow visible accordingly. At this point, we can simply break, as there is nothing more to do. Of course, the animation will continue to play as normal. This method of dealing with animation may seem a little complex, but it's actually very helpful, and we may use it a lot during this small series. Now back to the update method. You can see that I set the time when we should show the bow in the equip bow animation to 0.15. I obtained this exact time by playing the animation clip in the inspector, as I showed you earlier. Next, if the player presses the H key on the keyboard, we play the disarm bow animation and we set the time correctly to hide the bow. To enter the aiming mode, the player needs to hold down the right mouse button. If the right mouse button is released, the aiming boolean is set to false, indicating a transition to the equip bow pose state. We'll discuss this line further when we talk about IK. Finally, we set the aiming boolean parameter in the animator controller based on the aiming boolean variable we create here. In games, when the player is aiming, the camera's position usually changes smoothly, moving forward and to the right or left depending on the game. I created a separate function called aiming behavior to handle this smooth camera movement, and I called this function in the late update. If you watched my third-person camera tutorial, you already know that we discussed the late update method. The late update is considered a good place for the camera's behavior. Here, we simply check if the player has entered the reaching out area. We will talk about this later. If so, we simply return because with the reaching out example, we handle the camera differently. Then, if the player is aiming, we adjust the camera behavior accordingly by calling the aiming behavior. Otherwise, we go back to the normal camera behavior by calling the normal behavior. Now let's see what happens inside the aiming behavior function. First, I modify the camera's position by smoothly interpolating from the current position to the new aiming position, as well as the height of the camera. I chose these numbers by simply playing the game and changing the camera position in the scene view. Once I got the result I wanted, I copied the numbers and pasted them here. We could also change the camera's field of view, FOV, to make aiming more realistic, but I did not do that here. You could easily do that by accessing this property on the main camera. Finally, I reduced the mouse sensitivity to half. This is common in games and will help make the aiming experience much better. Also, while aiming, we need to make a couple of adjustments to the player controller. First, we should slow down the player's movement while aiming. I simply created two variables for speed, one for aiming and the other for walking, and set them in the update method. The third-person controller is quite simple. The character stays still and only follows the camera's direction when moving. However, if the player is aiming and tries to rotate, we need to accommodate this by rotating the player. Although this isn't the ideal approach, if we were to implement an advanced third-person controller, we would use turn-in-place animations. Since we don't have such animations here, we can simply rotate the character using quaternions based on the camera's rotation. Now back to the aiming handler script. In the fixed update, we calculate the aiming direction based on the mouse position. We start by creating array from the camera through the mouse position. Screen point array. This method creates array starting from the camera's position, passing through the specified screen point, mouse position in this case. It is appropriate for converting screen coordinates to world space. Then we use ray casts to check if the ray hits an object within the specified range and the aiming layer mask. I draw a couple of lines and rays to visualize the aiming direction, shooting direction, which I will show you this in the scene view. Here we set the target position to the hit point, but this for the IK aiming constraints which we will discuss later. And the last thing I do here is creating a function to return the shooting direction. The shooting direction starts from the character's right hand because the character will be holding the arrow in her right hand. This will make the direction of the projectile motion more realistic, and I will demonstrate it shortly. Before we test this, let's quickly review the shooting mechanic. First, I'll show you the arrow prefab that we need to spawn. The arrow is a game object that I've rotated according to the character's right-hand rotation. This is important so that the arrow is oriented correctly towards the shooting direction. Although we will handle this rotation in code at the time of shooting, setting it up this way initially ensures that it's correctly rotated from the beginning. If you're wondering how I obtained these rotation angles, I simply attached the arrow to the character's right hand in the scene view and then rotated it accordingly, and then I copied the result. The parent game object has a rigid body component set to kinematics. We're not going to use forces for shooting, as it doesn't look good. Instead, we will use kinematic movement with interpolation for smooth motion. This will make the arrow's flight look more realistic and controlled, and we will add this script to the arrow in the code. Let's check this out. The shooting script needs to be added to the character prefab in the hierarchy. We require a couple of variables, such as the arrow prefab that we need to spawn and a reference to the character's right hand, so we can spawn the arrow as a child to it. We have two variables to control the arrow's speed and gravity to simulate a curved shape. We also need a reference to the aiming handler to get the shooting direction we calculated there. Finally, we have a variable to get a reference to the spawned arrow game object. If the player presses the left mouse button and the arrow game object has been spawned, we call the shoot arrow function. Before we talk about the shoot arrow function, let's quickly see the spawn arrow function. It's a public function, and this is important since we will call this function using animation events in the animation clip. The shoot arrow function adds the arrow projectile class to the spawned arrow and calls the initialize method. This method needs several animations such as the shooting direction, the arrow speed, and gravity. In the arrow projectile script, we manually control the arrow's trajectory by updating its position and rotation. We simply update the arrow position based on velocity and gravity and rotate the arrow to face the direction it's moving. In the Unity editor, I'll demonstrate how to call the spawn arrow function using animation events. It's important to ensure that the script containing the function is attached along with the animator component. We'll do this within the aiming animation clip. While playing the aiming animation, we'll pinpoint the exact timing to spawn the arrow. Once we find the perfect timing, we can create an event and select the spawn arrow method from the shooting script in the inspector. In the shooting script of the character's prefab, I set the gravity to 0, so the arrow will precisely follow the shooting direction. We'll adjust the gravity later and observe the difference. Let's test this and see the results of the aiming system without using any IK constraints. If you notice, there's a red line that extends from the camera to the hit point, representing the aiming direction. The blue ray extends from the right hand to the hit point, indicating the shooting direction. Additionally, the pink sphere represents the aim target, which we'll discuss later. Now watch carefully while I aim. There is no motion from the character's body, and the bow does not follow the aiming direction. This is obviously not natural and not realistic. Even though the shooting works just fine, the aiming experience is terrible. So let's fix this by adding inverse kinematics constraints. Before we see the constraints, if you don't know what inverse kinematics is or you haven't used Unity's animation rigging package, you should first watch the tutorial Weapons Equipment System using IK, and then come here, because I won't explain the package again. Okay, I have already set the rig and called it aiming rig and added it to the rig builder component. I set the aiming rig's weight to 0 by default. We will control when to apply the constraint and when not to in the code. We will set multiple constraints. We need the torso or the spine bone to bend and rotate correctly according to the aim target, as well as the left hand, which is holding the bow. To make the shooting look more fluid, we will add two more constraints, one for the right hand and the other for the right forearm. For all these bones, the constraint we will be using is called the multi-aim constraint. A multi-aim constraint is used to rotate a constrained object to face a target position specified by one or more source objects. This is commonly used in aiming systems for making a game object look at points of interest, such as interactable props or the position of the cursor. The aim direction can be specified by selecting the aim axis on the constrained object. World-up parameters can also be defined to help the constrained object maintain a stable roll orientation for smooth and realistic aiming behavior, although it may not be necessary in our case. To set up the multi-aim constraint, you need to select the aim and up axes for each constrained object. For example, if you select the spine one bone and ensure that you have selected the local gizmos, you can see the local axes. The axes for the spine one bone are similar to the world axes, but for other bones such as the hands, they may be different. Before going into how to set the source object, we need to discuss a few things. Now, regarding the source object, there are a couple of ways to set this up. I'll first show you the simpler and more effective method, as I tried the other option and it didn't work. Since we calculate the aiming point in the code using raycasts, we obtain this information at runtime, so it makes sense to handle it in the code. However, as mentioned, that method didn't work out. Don't worry, we'll explore the other options soon, but for now, let's focus on this solution. We can create an empty game object called aimTarget and set it as the source object for the multi-aim constraint in the inspector from the beginning. Then, in the code, once we determine the aiming point, we can adjust its position accordingly. This approach works well and achieves the behavior we're aiming for. The aimTarget game object is the pink sphere you saw in the game a little earlier. We'll explore the other method when we dive into the code, but first, let's go over the settings section in the multi-aim constraint. These settings are very useful. For instance, the offset vector specifies an additional local space rotation offset to apply to the constrained object after it has been rotated toward its target. For the spine 1 bone, I've set the Y rotation to 90 degrees. Sometimes, when you download animations from Mixamo, they don't behave exactly as expected. After applying the constraint, you might notice that the spine is not rotated correctly in play mode. In that case, you can adjust this offset vector and set the appropriate value here. You can apply similar adjustments for other bones, such as the left hand, and right forearm. The constraint axes specify which axis the constraint can apply rotation to. For this constraint, we want the rotation to be applied to all axes. We can also clamp the minimum and maximum rotations that can be applied along any of the constrained rotation axes. For the right forearm, you'll notice that the aim and up axes are completely different from the world axis. To verify this, you can select the right forearm bone and check the local axis. Here you can see that I've changed the offset rotation. Let me quickly explain how I determined these values. In the Animator window, I set the aiming animation as the default state so that it plays automatically when the game runs. In the scene view, you can adjust these offset values, and once you're satisfied with them, just copy them. Now let's return to the aiming handler and examine the changes we need to make to enable the constraints correctly. First, we need a reference to the aiming rig, along with another reference to the character's right hand transform. We need the right hand to calculate the shooting direction, which we've seen earlier. Now we just need to determine when to enable and disable the constraints. We can use the existing Boolean called as aiming. If the player is aiming, we set the weight property on the aiming rig to 1. Otherwise, we set it to 0. We'll use lerp to smoothly enable or disable the influence of the constraint on the character's body. Finally, in the fixed update, when the recast hits something, we retrieve the hit point position, which represents the target position, and set the aim target's position accordingly. Remember, this aim target game object is the target we set in the inspector as the source object for the multi-aim constraint. That's all. Everything should now work as expected. Before we check the final result, as I mentioned earlier, there's another way to set the source objects directly from the script. Let's quickly go over that. I won't go into detail since it didn't work, which seems to be a common issue where the source object is set correctly, but the constraints fail to function. The first option is much simpler and works perfectly. This alternative method requires a couple of variables. The source object's variable is an instance of weighted transform array that holds the target transforms. The weighted transform array is used to manage a collection of transforms with associated weights, enabling smooth blending between different target positions. In this script, we also have references to the multi-aim constraint for the right arm and the multi-aim constraint for the spine, which we would set the source objects for. The rig builder is a component that manages the rig. We create a small sphere game object named aimTarget, similar to the one we already have, but this time we create the entire object from the script to represent the mouse position in world space. The aimTarget is then added to the source objects array with a weight of 1.0f. The method update constraints source objects is called to apply this target to the constraints, ensuring that the character's right arm and spine aim at the aim target. The update constraints source objects method is responsible for updating the source objects of the multi-aim constraints and re-enabling them to ensure they are applied correctly. It assigns the source objects to both bones, clears and resets the source objects to ensure they are assigned properly, and sets their weights to 1.0f. The constraints are then disabled and re-enabled to refresh their state. If the rig builder component is present, it rebuilds the rig to apply the changes. This ensures that the constraints are continuously updated, allowing the character's right arm and spine to accurately aim at the aim target. I tried many options while experimenting, but none of them were able to make the constraints work correctly. Anyway, let's now take a look at the final result together. Excellent. You can see how the entire aiming experience feels more natural and fluid. The spine and both hands are rotated correctly, and the bow is following the aim target as intended. The arrow follows the shooting direction smoothly as well. Let's add gravity to the arrow's motion to create a curved trajectory. Currently, the arrow won't hit the target directly when applying gravity, but we might be able to increase its speed to achieve this. Ultimately, it depends on the game design. There are still some other adjustments we can make to enhance this aiming system's realism, but for now, it already looks pretty good. I'll leave any further adjustments to you. Now it's time to explore another example. You saw a glimpse of this in the intro. It's subtle but very interesting. You'll definitely appreciate the final result as you see the difference before and after adding IK. I've set up a simple area with some ancient ruins to demonstrate this example. We have a single reaching out animation that we'll look at shortly. We'll achieve this by adding a trigger bound, so when the player steps into it, we handle all the logic. This is typically how it's done in games. As you can see, the trigger is very thin because I want the animation to align correctly with the ruin. We could make the trigger cover the entire area, but then we would also have to deal with root motion in the walking animation, which isn't necessary here. When the player steps into the trigger, we stop all controls until the animations and IK are finished. The player can press a button to exit and return to the normal locomotion state. Notice how the camera smoothly moves forward. This is the final result using IK. You can observe how the right hand is positioned and moves correctly on the ruin. There's a lot to discuss here, but we'll save that for later. For now, we want to implement the setup using only animations so you can see the difference. Let's quickly review the animations we have in the Animator Controller setup. It's quite simple. We only have a single reaching out animation. In the bottom right, you can see the animation, where the character's right hand slowly reaches for an object as the character examining something. It's a great animation clip for our example, but you'll notice that the character's right hand almost moves in a straight line, which we'll address shortly. This animation clip also has root motion. You can see the bottom circle at the character's feet moving as the animation plays. I've adjusted some of the root motion settings we discussed at the beginning of this tutorial. I encourage you to experiment with these settings to better understand the changes they make. For the Animator Controller setup, as I mentioned, it's quite simple. I created a new substate machine named Reaching Out and placed it in the upper body layer, as before. This substate machine includes the Reaching Out animation clip. No parameters are used here for transitioning to the Reaching Out clip since we play the animation clip from code. Once the animation finishes and the player exits the trigger bound area, the animation transitions to the exit state by triggering a parameter trigger called Exit Reaching Out State. Now, let's take a look at the code responsible for hooking everything together. As before, we'll start by understanding what each variable is used for. I'll focus only on the ones we need so far. We'll cover the IK variables later. First, we need a reference to the camera controller to modify the camera's behavior. We also need a reference to the player controller to stop the character's movement while the reaching out animation occurs. Additionally, we require a reference to the player's animator component to play the relevant animation. Finally, we need a Boolean variable to indicate whether the player has entered the reaching out area. This Boolean is necessary for performing the exit state when the player presses the exit button. Since this script is attached to the trigger bound, we can use the onTriggerEnter method to handle most of the logic. If the player enters the reaching out area, the first thing we do is stop all the player's controls. We achieve this by invoking the entered reaching out trigger bound event, which is created in the player controller, with a value of true. Let me quickly show you this event in the player controller. In the player controller, I declared an action with a Boolean parameter and created another Boolean variable called has entered reaching out trigger bound to store the value sent from the reaching out class. In the start method, I subscribe to a method called enable has entered reaching out trigger bound, which is responsible for storing the value sent from the reaching out class. In the update method, if this value is true, we simply return, preventing any further instructions from being executed. Back in the reaching out class, once the player steps into the trigger bound, we play the reaching out animation clip using the crossfade method with a transition duration of 0.2 seconds. That's all for now since no IK is included yet. One last thing to note is that in the update method, when the player presses the E key on the keyboard, we trigger the exit reaching out state, set the entered reaching out area Boolean to false, and finally send a value of false to the player controller so the player can move freely again. Now, let's give it a test. Also, let me quickly show you the reaching out camera behavior. It's quite similar to the previous behaviors. We smoothly pull the camera forward and a bit to the right and lower. Watch what happens when no IK is applied. The player enters the trigger-bound area, the player's controls are completely stopped, and the animation plays. It feels static and unnatural. Additionally, the player's right hand moves in a straight line, which doesn't meet our expectations. Imagine needing a different keyframed animation for each scene where the player's hand must be in a different location. It's not practical and can be expensive. With IK, we can achieve multiple behaviors with just a single animation, as you'll see shortly. But first, let's discuss how we'll position these locations. If you remember, when I showed you the final result at the beginning, the player's right hand was placed correctly and moved smoothly from one location to another. I'm going to show you two different methods for achieving that. Let's get started. In the first method, we'll create two different locations and position them as desired. For example, I placed them slightly at the edge of this ruin and stacked one underneath the other. In the code, we'll smoothly interpolate the player's right hand between these two locations. By the way, placing these locations is quite simple. After we implement all the IK logic, as we usually do, you can play the game and then position these two location game objects in the scene view as you prefer. After that, you can simply copy their transforms. Before we move on to the second method, let's first take a look at the IK rig and constraints. We will use multiple constraints here. After we see the result together, I'll show you the second method, which I believe is the better option. I created a new rig called Reaching Out Rig and set its weight to 0, as we want to control when to enable the constraints through code. I also added this rig to the rig builder component on the character game object. For the constraints, we need a 2-bone constraint for the right hand. We've discussed this constraint in detail in the previous tutorial, so if you haven't watched that yet, I recommend checking it out first. The target game object is what the hand will follow, so we need to position this target accurately based on the hand locations we created earlier. To enhance realism in this example, we will again use the multi-aim constraint to ensure that the spine bends and rotates towards the target location. We'll also add a multi-aim constraint for the head, allowing it to bend towards the target as well. We previously discussed how to set these constraints up, but one important note is that I didn't set the weight properties for both the head and the spine to 1. This is to ensure that their influence on the body is smooth and subtle. Now, let's take a look at the code and the changes we need to make to achieve this behavior. First, we need a reference to the Reaching Out rig so we can enable the constraints by adjusting the weight properties. We also require a reference to the character's right hand target, which is the game object we'll position according to the hand locations, allowing the character's right hand to follow correctly. Next, we have a list for the hand locations. I chose to use a list because we could be having more than just 2 hands location. This is totally up to you. We also need a boolean to determine when to enable the rig and when not to. The finished waiting boolean will become important later, and I'll explain its purpose once we dive into the code. In the onTriggerEnter method, we set the rig to enable it to true. However, instead of playing the animation clip directly as before, we'll need to wait until the character's right hand has moved at least halfway to the target before enabling the constraints. This is crucial because we want the entire scene to feel fluid and natural. If the constraints were enabled by default, the character's right hand would come across as stiff and rigid. Let's take a look at the Enable Constraints coroutine method. It's similar to the bow visibility method we discussed in the aiming example. In this method, we play the animation, wait for a single frame, and then wait for the right moment to enable the constraints by setting the Enable Rig boolean to true. In the update method, we'll set the weight of the Reaching Out rig. We only do this if the Enable Rig boolean is true and the player is still within the reaching out area. Let me uncomment those lines of code. Remember that we have 2 hand locations, and we want the character's right hand to reach the first hand location, wait a couple of seconds, and then smoothly move to the second hand location. That's why we need the finished waiting boolean variable to control this process. As long as this boolean is false, we set the right hand target position and rotation according to the first hand location. We achieve the waiting period by using a simple delay coroutine, which waits for 2 seconds before setting the finished waiting boolean variable to true. Once it's set to true, we smoothly interpolate to the second hand location. Now, let's head back to the editor and see the result together. It seems I forget to uncomment the line responsible for setting the weight for the rig and therefore enable the constraints. Let me quickly do that, and then we can test this again. The current result looks okay, but it's not perfect. There's a slight hand penetration into the ruin, and the movement isn't as smooth as expected, even though we're using lerp. This leads us to the second method, which I think is simpler and more effective. Instead of creating two hand locations and interpolating between them in the code, we can create a single target game object and an animation clip for it to move in any direction and manner we prefer. Let me demonstrate that for you. I've created a small sphere. Let me enable the mesh renderer and give it a different material so that you can see it clearly. The initial position is set correctly, and you can place it wherever you want. Then we'll create a simple animation to move this target sphere. Since the right hand is constrained based on the right hand's target, all we have to do in the code is set the right hand's target position and rotation according to the target sphere. The animation will wait for a couple of frames, and then we'll move the target to another location slowly and smoothly. Let's quickly make some changes in the code. First, we need a reference to the target sphere game object and its animator component so we can play the animation. We don't need all the code we had for the first method anymore. We can simply comment it out. In the onTriggerEnter method, we go back to playing the animation as before and also play the target sphere animation at this point. We don't need all these lines of code in the update method. So, I will simply comment them out, and instead, we set the right hand's target position and rotation according to the target sphere. And that's pretty much it. Now let's test this final result together and observe the difference. Excellent. This looks pretty good. The right hand is placed correctly and moves smoothly. Notice how the elbow bends correctly. Both the spine and the head rotate smoothly. We could perhaps adjust the weight property and angle of rotations a little, but it looks good enough for now. If I press the E key on the keyboard, the player will exit this area and go back to its normal locomotion state. I plan to showcase all 4 examples I've prepared here in this video, but we'll save the rest for the next one. In the next video, we'll cover more animations and new IK constraints. For instance, the follow-up example is really interesting. We'll be implementing this example using a bit of math and the override transform constraint. For now, thank you for watching and see you in the next video.